All right. Well, hello. Happy Wednesday. Happy Wednesday, week 4. Who is anyone here doing Data Fest this weekend? Oh, all right. All right. That's exciting. Huh? Well, wait. When's the homework due?
Friday.
It's due Friday, right? Before Data Fest starts.
Friday, Data Fest starts on Friday.
Yeah, so you'll be done with your homework and then you go to Data Fest, right?
Exactly.
So, okay, so yes, you don't have to study for Data Fest. You just show up, okay? It's not like I have to study for Data Fest. No, you just show up and then you have fun. So yeah, so finish your homework, then go to Data Fest. I'll show up on Saturday, and I guess, I don't know, I signed up as a quote mentor, which just means I'll help answer and troubleshoot problems you encounter. Who wants to, anybody here planning on doing Data Fest on Python, in Python? That's like, you're gonna learn Python when you try to do Data Fest in Python. But unfortunately, I haven't even like covered how to do, what do you call it? Pandas in Python, which is going to be hard to do Data Fest without pandas. So I guess if you want to study, for Data Fest, go to Data Camp and do the Python modules. But you can also do that while you're in Data Fest. You know, you got 48 hours. Yeah, learning on the job. That's what's going to happen in real life anyway. When you get your first real job after college, there's going to be a lot of learning on the job. All right, well, anyway, we're talking more NumPy today. So we introduced NumPy on Monday. NumPy is basically the package that introduces this data structure, the array, the NumPy array, which is, very similar to R's vectors and matrices. And they contain just one data type. And one advantage of using NumPy arrays over a list in Python, because a list in Python is actually a lot more flexible, okay? But one thing that using a NumPy array does in Python is that it really, really, really speeds up computations, which becomes important when you're doing stuff like machine learning and you have these huge matrices with millions of values in them. If you were to try to do the computations in a list, those computations would be very slow. By using NumPy arrays, they happen very quickly. And we're not going to cover this, but you can also install these kind of additional packages that take advantage of, if you have I don't know if you have a gaming laptop or of a desktop PC and you install like these GPUs, okay, which are used for like gaming, and because there's like billions of computations happening every second in a gaming PC, but also you have these like these libraries that are able to kind of split up these giant matrices and use kind of the processing power of a GPU to speed up your calculations, which is nice, but that's beyond the scope of this course. Not everybody here even has a laptop capable of doing stuff like that. Most laptops just have a plain, very simple GPU. It's not designed to play fancy video games on there, right? So unless you specifically, you would know, and you'd probably have a Rainbow keyboard if you did. So I don't know why Rainbow keyboards became the thing of gaming, but somehow, I don't know. It's like you have to have one. All right, anyway, let's talk about just kind of like taking arrays and then sticking them together, concatenating them. So here I've got two arrays. I've got x and y, they are both one-dimensional arrays, okay? One-dimensional length 4 arrays. And you can call np numpy.concatenate. All right, so again, we import numpy, and just to kind of save us, I guess, 3 keystrokes, we abbreviate it as np, okay? But that's what we do, np.concatenate. I guess you could type numpy or np with just one hand either way. But anyway, np.concatenate will join the 2 arrays together. And so when you do this, it will join them together. Now you get an array of length 8, 0, 1, 2, 3, and 100, 101, 102, 103 joined together there, okay? If, so the default, okay, the default is to kind of just join them on axis 0. Now remember, the dimensions, if you ask what is the shape of x, it's going to just be 4 comma. It'll be a tuple, length 4, and it's just one-dimensional. So as far as, I guess if you draw a line, and you have 2 lines, and you say join the lines together, you can only just make the line longer. You can't stack one line on top of another because they're one-dimensional, right? And it's kind of like that. So anyway, you can specify the axis upon which you want to join the arrays, but in this case, there's only one thing. If you try to join them in a different axis, right? So if you say, hey, join them the other way, you get an error, right? It says you can't take a line and stack another line on top of that. Okay, you've got to give it some width, right? Because if you ask what's the shape of x, it's just this tuple 4 comma, something like that. Now, what you can do is you can call vstack, okay? Vstack, vertical stacking, will turn this, it will suddenly give that one-dimensional array and turn it into something that can be stacked, okay? And you can, if you call vstack on that. Another way you can do this is you can take x and you can reshape it so that now it's a 1x4 array, right? And the way we can tell when you look at the array is that you've got these 2 opening square brackets here. And when you see the 2 opening square brackets, you know it's a 2-dimensional array. So it's now 1x4. And if we take this 1x4 and a 1x4, then we can concatenate them, or we can also concatenate them along the other axis. So here I'm going to call numpy concatenate with the reshaped 1x4 array and the reshaped y, which is also 1x4. And here I can concatenate them along axis 0. So, well, all right. So what's happening here? So I got x. If this is if you think about what is the shape of x, its shape is 1, 4, right? And so this is axis 0, and this is axis 1. So here, if I have y, which is going to be 100, 101, 102, 103, again, its shape. So when I say concatenate along axis 0, we're going to take this one and add that one, and so the result is going to be a 2x4. Okay? If I say concatenate along axis 1, then we're going to join the 4 and the 4, and we'll get a 1x8. Okay? So that's what you have there. When you only had, when x was just one-dimensional, okay, and the shape was just 4 comma, then concatenating along axis 0, concatenating along axis 0, well, there's only the 4 and the 4. So that's going to, that's why concatenating along axis 0 is going to make it at length 8, okay, when it was one-dimensional. All right. All right, so here, let's make a matrix xm and ym. And these are both 2 by 3 matrices. So I can say, what's the shape of x? It's 2 by 3. What's the shape of ym? Also 2 by 3. Okay, so what will the resulting dimension be when I say np.concatenate? Default is going to use axis 0. So am I going to get a 4 by 3 or a 2 by 6? NumPy.concatenate. We're going to concatenate xm and ym. Oh, I have to. Okay, while you guys think about that, let me set up our view quiz because I don't think I have it set up yet. Or do I? No. I was too busy with my midterm for the other exam, or other class. Okay, so do we have an answer? Concatenate the default. Is that the right time? No, available from 10 a.m. We got to change that. Available. Okay, I'm going to do 8:59. Okay, so we look at the shape, and axis 0 is going to refer to the 2. So when we concatenate those, we will get a 4 by 3. Okay. When I say, if I specify axis equals 0, we'll get the 4 by 3. And if I specify axis equals 1, then we will join index 1, which is length 3 and length 3, then we'll get a 2 by 6. Okay. You can also call VStack and HStack. VStack is basically stack them vertically, so you get the 4 by 3. HStack is going to stack them horizontally, and so you get the 2 by 6. So you can also call VStack and HStack as a as a way to do it. Okay, let's go back. Let's just do some. Well, I guess maybe I should just pause, make sure we're okay with the VStack, HStack concatenating of the arrays. Just because as you get like more and more data, so you might, your data might be stored in some kind of matrix, and it's not unusual to say like, okay, I've got additional data and I want to join that up with my currently existing matrix. And so probably you'll use VStack, but unless it's like, oh, here's a new column of values, then yeah, HStack. Okay, here's X and Y. Math operations, when you do something like +5, X plus 5, it's going to kind of repeat that +5 across the board. So 0, 1, 2, 3 becomes 5, 6, 7, 8. If you just do plus or star, then you'll get element-wise multiplication. So 0, 1, 2, 3, and 100, 101, 102 because this 100, 102, 104, 106. X times Y gives us 0 times 100, 1 times 101, 2 times 102, 3 times 103, element-wise multiplication. You can you can do element-wise multiplication and then sum them up. That is also known as the dot product, right? You take two vectors and you multiply their elements and add them up. So you can call numpy.sum on x times y, or you can just do numpy.dot, which I guess sounds kind of funny, numpy.dot x comma y, and it will do the dot product. And then you also have, sorry, I'm one moment here. Okay, you have the at symbol, which does matrix multiplication, and you can, I guess when you have two vectors, it will automatically kind of align them in the way that needs to be, right? So here, x and y are just these one-dimensional arrays, They're not a row matrix or a column matrix, but the @ symbol for matrix multiplication allows us to kind of do it. So these all, yield the same values there. Okay. All right, here I have our matrices, our 2x3 matrices. Same thing, doing a plus, we'll do it, repeat it across the thing. If you do addition, you'll get element-wise addition between these two matrices. Let me just repeat this. If I do multiplication, we will get element-wise multiplication. You also have numpy.multiply, which does the same kind of thing, element-wise multiplication. You might ask, why would I want to do np.multiply versus the star? Okay. But you have, when you do np.multiply, there are just kind of additional arguments. Some of these might be useful, but I don't know. For a lot of these things, we don't have to worry too much about them. But yeah, you have additional arguments when you do something like numpy.multiply. If you can call dot numpy dot, all right? And so here, this is kind of like doing, you'll have to transpose one of them, okay? So you'll do y, because if you try to do this, you'll have to do the transpose, and let's see, xm.ym.transpose. Oh, okay, yeah, sorry. So here you can also call the dot method on the matrix itself. So you can do xm dot rather than numpy dot and give it the names of the two matrices. You can do x matrix dot and then put in the other matrix. Okay. All right. So we'll keep looking at this. All right, so here is just some additional kind of math operations. Here I've got a simple array, 0, 1, 2, 3. You can do +4, addition, subtraction, multiplication, division, make everything negative, raise everything to the power. You can also do modulo division. You can do absolute values. So these are all kind of just basic operations. And whenever you do those operations, they apply across the board to all of the values in the array. So I don't think any surprises there. Okay. NumPy also has a bunch of kind of math operations. If you are going to use any of these math operations, they also exist in the math package. However, if you are using NumPy arrays, I recommend using the NumPy functions, right? So you have like math.sign, which I think you used in one of your homework problems and something like that. But here you're going to do numpy.sign, and and they pretty much behave the same way, but you will get better performance by using numpy.sign. The NumPy functions have some internal things going on that are optimized to work with NumPy arrays. So you're just going to get faster performance overall. Okay, so here I've got an array linearly spaced from 0 to pi, length 5. So basically we're going to go 0, pi fourths, pi halves, 3/4 pi, pi, right? Okay, so we have that. And then, so if you call sign on this, what are you going to get? You'll go from 0 to, what is this, root 2 over 2, 1, root 2 over 2, and basically 0, because of, what do you call it, floating points. You get something on the order of 10 to the negative 16, which in computer speak basically means 0. Okay, cosine, same kind of thing, 1, root 2 over 2, 0, negative root 2 over 2, negative 1. Tangent, look what happens here. You get 0, 1, and then again, this is not infinity, it's 10 to the 16. That's a far cry from infinity, but it's a big number, and I guess that's what our approximation is. Okay, and then -1, and then almost 0. All right. Similarly, we have log functions. So you got numpy.log. Log is always going to be natural log. And then if you want a common log, base 10 log, you call log 10. Okay, so you have that. So here, if I have 1, 10, 100, you know, the base 10 log gives us 0, 1, and 2. Here, I've got, you also have the e function. Numpy.exp is going to raise it to the e power, so raising it to 0, 1, and 2. You can, there's also exp2, that's going to be 2 to the whatever, 2 to the y. So that will give us 1, 2, and 4. And then if you want, there's just a generic power function. You put in whatever base you want, and you'll get that as well. Okay, let me give you your first view quiz answer. Today, the first answer is the letter A. A as in apple. A. All right. If you want to call sum, all right, you can take an array and sum up all of the values. So if I do 0 through 99, I can say, hey, what's the sum of this? And we get 4,950, right? What is that? N times n plus 1 over 2. That's the formula. Okay. The next, so that's just regular old sum. You can call numpy.sum, okay? And that also yields 4,950. I'm going to skip this thing. This is, there is this what we call a magic function, %time it. You can run it, but it'll clog up your computer for a little bit. What it does is it has the computer repeat an operation like a million times. It'll probably take 20 to 30 seconds for it to run, and it will time how long each of those things take. And what you will find is that the calculation time for regular old sum, the built-in sum function, versus the numpy.sum function is that the numpy sum function just operates much faster. Okay, and that kind of time difference is noticeable when you have like a big array, like I've got random values, 10,000 random values. Okay, you can also ask, whoops, I guess I do have to run this, but I'm going to just comment these out. So here's my big array. So you can also ask, hey, what's the max and the min of these things? There's also numpy.max and min and max. The numpy version, again, is much faster than the built-in min and max function. So you can try running those. Has anyone tried running it and it's clogging up your machine for a few seconds? But it'll spit out. And one is generally on the order of 10 to 100 times faster than the other. If you look at, because one will be measured in like microseconds or milliseconds, and the other one will be measured in like nanoseconds. Okay. All right. Similarly, we can do some operations on matrices, right? So here I'm just going to take the integers 0 through 11 and shuffle them up. So there is a function in numpy.random called shuffle, and basically it just takes the values and mixes up the order. It's very simple, similar to in R you have sample, and if you do sample and you don't specify replace equals true, you leave it as replace equals false, it will just take your vector and just shuffle them up. And that's basically what we've done here. I've taken M is a vector or a numpy array of length 12, 0 through 11. I shuffle them up and then I reshape them into a 3x4 matrix or a 3x4 numpy array. I can say, hey, what's the sum of these things? If you call sum, this is a little bit strange. The default behavior of the built-in sum function will give you column sums. So 2 plus 1 plus 11 is 14. 3 plus 6 plus 9 is 18. So that's a little bit odd, in my opinion, that when you call sum on an array. The numpy.sum function, I think, is a little bit more reasonable, and it just adds up all of the values in the matrix and gives you one value, 66. So that's what we have there. You can also specify along which axis you want to do the summation. So here, I have this this array, and it's 3 by 4. What is it? 2, 3, 2, 3, 1, 11, so on and so forth. Okay, so it's the shape is 3 by 4. So when I call axis equals, when I say sum along axis equals 0, it is summing across the 3 rows. Okay, so the result. Okay, so when you say sum axis 0, basically we are going to collapse the 0 axis. Okay, and so now the result is going to be a 1 by 4 when you say sum across axis 0. Okay, so that's going to be the result there, but it's not the result's not 1 by 4. It's just going to be, I guess, length 4, 4 comma the result there. So if I say axis equals 1, it's going to sum across the length 4. Okay, and we will get 2 plus 3 plus 4 plus 10, and that will give us what, 19 there. Okay. Similarly, you can call functions like the min, the max, standard deviation, any of these other summary functions. Any function that basically takes a set of values and returns 1. Okay, so here this will be give me the minimum. Okay, and collapse axis 0. So between 2, 1, and 11, what's the minimum value? Between 3, 6, and 9, what's the minimum value? Between 4, 0, and 8, what's the minimum value? Between 10, 7, and 5, what's the minimum value? That's what we have. Okay. Here's our 3 by 4 matrix again. You can say, hey, give me the standard deviation. Standard deviation will give you the standard deviation of all 12 numbers. Standard deviation axis equals 0 will give you, collapsing the 0 axis. Okay, collapsing the rows into 1. It will give you 4 standard deviation values. And then you can also say, what's the mean? The mean axis equals 1 will give me 3 values. So basically 2 plus 3 plus 4 plus 10 divided by 4. So that will give us what, 3.75? Or I'm sorry, 4.75? Something like that, okay? You can also do the same kind of thing. Here's a higher dimensional array. So here I'm going to have a 3-dimensional array. The shape is 2, 3, and 4. Okay, so when I say, so let's see, let's check our understanding here, okay? So basically I have the shape is 2 by 3 by 4, right? If I say axis equals 0, sum axis 0, what is the result going to be? So we're going to collapse this, okay? We're going to collapse this down into 1, and so the resulting dimension is going to be 3 by 4, and every value inside there is, because we're adding 1 and 1, we're going to get a bunch of 2's arranged in a 3 by 4, okay? Okay, what if I say axis equals 1? The result will be, so we're going to collapse this. The result is going to be 2 by 4, and we're going to have a whole bunch of 3's. Okay? And then if you say axis equals 2, we're going to collapse this one, and the result will be 2 by 3, and we'll have a whole bunch of 4's. Okay? Does that kind of make sense as far as how you specify the axis when you do something like numpy.sum? Right? Because sometimes you want to work with some kind of big, higher dimensional array. These are called tensors in Python speak. So if you have like this higher dimensional array, rather than just call them matrix, they're known as tensors. And I don't know, a lot of kind of machine learning, neural network stuff runs on tensors. And there's a well-known package, TensorFlow, which deals with that. And Google is dealing with their tensor processing units. They're creating their own specialized hardware for handling these types of arrays. Okay, that's what we have. All right. NumPy also has nans, and you can kind of create nans directly. So in Python, you call float nan, and that will create the nan. And when you do that, that's nan. So nan is used as a place for values that are not a number. So kind of indeterminate forms of things. Floating point numbers also have representation for infinity and negative infinity as well. Okay, so you can also create direct creation of the infinity by calling float infinity. Okay, and you can see computations involving infinity can result in nans as well. So if you do like y divided by y, like infinity divided by infinity, you get a nan. Infinity minus infinity gives us a nan. But if you do something like 7 minus infinity, you'll get negative infinity. Certain things will not, like you can do calculations. So if you take 4 divided by infinity, you'll get 0 or something like that. So those results are fine, but infinity over infinity results in nan. Okay. So remember, x is nan, and if I try to do sum, numpy.sum, and I say x and 2, the result is going to be nan. Okay, so anytime you do some kind of operation you have that involves a nan, the result is going to be not a number, right? It's like, hey, here's a mystery number, and add the number 2 to it. What's the result there? And it just says, I can't do that. Okay. So we have basically nan sums. We have functions that are nan safe versions of these things, and basically that just tells Python, hey, ignore any time you encounter a nan and just pretend those numbers don't even exist as part of your data set, and just do on the remaining operations. Okay. So basically all of these things, basically it just ignores them. So if I do np.nansum and I have nan 2, 2, and 3, and I say, hey, what is the mean of this? Okay, it's going to just, I'm sorry, not nansum, I want nan mean. Okay, it's going to just pretend like I have 2 numbers. Okay, so even though I have 3 values in the array, x, 2, and 3, it's going to just ignore the x and you say, hey, you only have 2 numbers, 2 and 3. And again, you can have multiple nans, and it ignores all of them. Okay, so same. So these are your regular kind of function names, and these are the nan safe version of these things. So it's kind of like na.rm equals true in R. You have that, right? All right, we have broadcasting. Okay, oh, it's already 9:40. Jeez. Second view quiz answer is the letter A. Second view quiz answer is the letter A. Okay. So we have broadcasting, and this basically kind of recycles elements here. So here I've got A is 1, 2, 3, and B is 4, 5, 6, and I can just do A plus B. Okay. If you have a vector or an array that's a shorter length and not a kind of a multiple or something like that, Python doesn't like it. Okay. So so here it says you got a length 3 and this is a length 2. I can't broadcast these together here. Okay. Look what happens here though. Okay, I'm going to build E to be a 3 by 3 matrix of 1s. Okay. So now I can say, hey, do E plus A. E plus A. And what it does is it takes that A and it broadcasts it across the rows. So you're going to get this top row plus 1, 2, 3, the second row plus A, which is 1, 2, 3, and the third row, which is 1, 1, 1, and 1, 2, 3. And basically what it has done, it has broadcast that across the rows. Here I'm going to reshape A to be 3 by 1. And I'm going to say E plus A here. And now that 1, 2, 3 down the column is going to get broadcast. And so now the top row becomes 2, 2, 2. The next is 3, 3, 3. And the bottom is 4, 4, 4. Right? So Python calls this broadcasting, where it basically takes an existing kind of lower dimensional thing and it broadcasts it across all of these things. Right? Here I have D is a 2 by 3 matrix. A is still my length 3 vector. Okay, so the default behavior is to broadcast across rows. So we're going to repeat 1, 2, 3 across the first row, 1, 2, 3 across the second row. Okay. Here I've got a length 2 vector, C 7, 8, and D is again 2 by 3. Now, if I try to do this, if I try to do D plus C, Python's going to complain. Okay, it's going to say this one is 2 by 3. This one is just a length 2. I don't like that. Okay, but what you can do is you can turn this 7, 8 into a column, right? So I'm going to reshape it into 2 by 1, and then I can broadcast it. Okay, and so so if you think about what is D being 1, 2, 3, and 4, 5, 6, basically I can just make it vertical, and I can add 7 across the top, and I can add 8s across the bottom. All right, is that okay? The reshape and then the adding there. So here's a couple interesting behaviors of this broadcasting. Here I have E, which is 10 by 1, and I have F, which is length 11. You can also broadcast these together, all right? So one is, you don't always have to have a matrix. You can just have kind of these two, well, I guess this one's a matrix, but it's 10 by 1. What Python will do is it will broadcast both of these simultaneously and combine them. So it's going to try to figure out how do we make this work? So it's going to say, okay, I've got this 10 by 1, and it's going to say the other thing is length 11. So I'm going to broadcast this into basically a 10 by 11, and then it takes this length 11 and it also broadcasts it into a 10 by 11. So the result is going to be this 10 by 11 matrix. Right? So this is like a very handy thing, but if you're not used to it, the first few times you use it, it can be a little bit confusing. So I recommend just kind of slowing down and taking your time and thinking about it, and then you'll say, ah, yes, this kind of makes sense. Okay. Same kind of thing. Multiplication. You can do a 10 by 1, and here the length 11. And if you do star, you will get basically a multiplication table, right? So I don't know, remember back in what, 3rd grade, you had to like fill this out by hand, and this was like your homework project or something? I don't know. But yeah, now we have this nice little multiplication table. They should include row 0 in the multiplication table. It feels silly, but that's just as important, right? But anyway, no multiplication table has the zeros there. Okay, here you can, I can take D, I'm going to reshape it into a 1 by 6, I'm going to reshape it into a 6 by 1, and you'll get something kind of similar here. So you can also take these kind of existing things. Again, this is kind of, you have to do some mental math here, and you have to say, well, what is this going to look like when I reshape it? And then you do that. Okay. We have these Boolean operators, and basically these will give us arrays of Boolean values. Okay, so here x is this array 0, 1, 2, 3, 4, 5. I can say, hey, do x less than 3. We're going to get this array of true, 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 false, false, false. Okay, all of these other things I think are no surprise. X greater than or equal to 3, x equal 3. And then once you have an array with true and false values, you can then subset based on those true and false values. So if I say subset x to using this Boolean array of x greater than or equal to 3, basically only the values that are true will get returned. Okay, so basically just the 3, 4, 5 corresponding values things here. Okay, these other behaviors, I think we're accustomed to. We've seen them already in R, right? So you do sum, it's going to convert the trues and falses. Trues become 1s, the falses become 0s. So you can do that. You call mean on a Boolean vector or a Boolean array. You'll get the proportion that's true. This is the one kind of, I guess, different symbol. The tilde is negation. So true becomes false, false becomes true. That's the operator. Okay, so that's going to, in R, it's the exclamation point. Python, it's, I should say NumPy, it's the tilde. Now, this is different. So Python also has a negation operator, and it's the word not. Okay, it's the word not. But that word not is used in your like if statements where you're expecting just one Boolean value. This is for NumPy where you have an entire array of Boolean values and you want that negation operator applied across the entire array, not just one thing that's showing up inside like an if statement or a conditional kind of statement. So if you get confused, you might be mixing up the not versus the tilde operator. Okay, this is something to get useful. Now you got to be careful here. Okay, if you do something like not x, all right. So here, let me just show you what is x. Okay, x is this array 0, 1, 2, 3, 4, 5, and if you call not x on this, basically, you get this kind of this weird thing, -1, -2, -3, -4, -5, -6, and it's like, well, what is happening there? So just be kind of careful about that. Basically, you want to apply the not. If there's like order of operations with Booleans, you basically want to apply the not last kind of thing. Okay. Ooh, all right. I gotta go fast here. Okay. So same kind of things with a matrix. You can also do the Boolean operators, and it's just going to create a matrix with all of these things. We have the sums that will give you how many true values total. You can also sum across axes and get like basically column sums here, how many trues, and same kind of things. You can also specify axis equals 1, and you get row sums on the Boolean thing. Okay. Here I'm creating these Boolean vectors, true, true, false, false, true, false, true, false. Okay, and these are what we call bitwise Boolean operators. These will take vectors or arrays of Boolean things and go element-wise, match them up, and compare them. This is different from the internal or and statements, which you spell out. So you can have true spelled out OR, false, false spelled out AND, false, things like that. Those are for conditional statements going inside your if and your while and things like that. But if you're doing something with NumPy and you want an array of these true, false things, then you use the Boolean operators, which we're accustomed to seeing, the ampersand for and, the vertical line for or, exclusive or is this caret. Okay, that might be fluke. So exclusive or basically means one has to be true and one has to be false in order for it to be true. If both are true, you'll get a false. If both are false, you'll get a false. Okay, we've already seen the bitwise not operator, which flips these around. You also have any and all, which looks to see if any of these things are true or if all of these things are true. Okay, again, these are reserved for dealing with NumPy arrays that are full of Boolean values. Okay, I'm going to skip out on fancy indexing. I'll let you read that on your own. Basically, you can just kind of say, hey, I want just the third element or the seventh element in some kind of thing. I want to pick out, within this row in that column. You have that. You have sort, okay, which will sort them and sorts them in place, okay. And then you have argsort, which will give you if I wanted to put these in order, which values do I want? So here I have 5, 2, 1, and 4. If I wanted to put these in order, the order in which I would do it is I would select the index 2 element, which is 1, then the index 1 element, then the index 3 element, then the index 0 element to put them into order from least to greatest. And then if you subset indeed on that argsort, you will get them in order from least to greatest. Okay. You can also take a matrix and you can sort them along the axes. Okay. So here I'm going to say sort along axis 0, and so you'll see this first column, which is 5, 1, 5, 7, becomes 1, 5, 5, 7. The second column, which is 8, 7, 2, 9, becomes 2, 7, 8, 9. So here I'm sorting along axis 0. You can sort along axis 1, which feels strange to do with a matrix, because this really breaks up, like, if each of these things were rows, it really kind of just breaks up any kind of association, one versus the other. So, but if you wanted to do that, you could, okay? And then you can subset selecting a row or something like that, okay? And so these are just different operators there. I guess I'll just say you can review these things. These are just, I think, good examples that point out some of the different operations there. All right, let me give you